Hello class, this is a video tutorial on network flow problems. In this video, we'll be learning about the minimum cut and the maximum flow. So, the following network represents the water pipe system from a dam to a rural city, passing through smaller towns along the way. The weight of each edge is the amount of water that can pass through that pipe in liters per minute. So we have the dam here and the rural city all the way to the right. And these pipes here represent the amount of water that can go through it. So this is 300 liters per minute, 500 liters per minute, and so on. Notice how these are directed edges, meaning that the water must flow only in one direction and they can't go backwards. Note how the two main flows of water are both limited along the way. So from the dam to the city, there's really only two ways you can get there. 1 and 2. But along the way, there are limitations. So they have two main parts, A, B, C, E, from A, B, C, E, or A, D, E. C, E, so the edge C to E, could have 800 liters per minute, but BC only provides 600 liters per minute. So this is actually restricted by BC. Same case for this. BC could have 600 liters per minute, but AB only provides 300 liters per minute. So the flow capacity of ABCE, so ABCE, so the maximum flow capacity of that is 300 liters per minute. So there's a restriction somewhere along the path. In this case, it'll be 300. For ADE, AD from A to D provides 500 liters per minute, but DE has a maximum capacity of only 150 liters per minute. So AD could provide 500, but DE can only take 150 liters per minute. So the flow capacity of this entire flow is 150. So these examples are what's known as the flow capacity, or you can think of it as a bottleneck in the system where it's restricted somewhere along the line. And now this is a simple example. In this simple example, we have identified the most amounts of water the town can receive per minute. So the town, even though there's 800, 600, 150, 500, or 300, the most that this town can ever receive per minute is 300 plus 150, because this path is restricted by 300 and this path is restricted by 150. So the most that town E, or the rural city, is receiving is 150 liters per minute. Now this simulates the problems of maximum flow, minimum cut, both of which can identify the carrying capacity, that number that we showed, so the maximum amount of flow in the entire network, as well as bottlenecks or choke points of a network. So in this case, the bottleneck was edge AB and edge DE. We can make a cut like this. These two are the bottleneck of this network. So let's get some terminology. As we continue in this unit of work, we're going to be identifying problems such as this, where we want to find the maximum flow and the locations of this flow. So we need to know now the source. The source is the origin of the resource. We're going to be looking at things like water, traffic, electricity. It could also be people, money, or whatever it might be. And the source in this example is the dam. In problems such as these, we assume that the source has infinite supply of whatever the resource is. The sink is the target destination of a problem. So in this example, the rural city is the sink because that is the target destination that we are focusing on. The flow capacity is the smallest value along a path from the source to the sink. So in this case, from the source to the sink, the flow capacity of this path is 300. The flow capacity of this path is 150. The maximum flow is the sum of all paths' max capacity, or the flow capacity. This also represents the entire network's maximum flow. To explain that one, that was the total amount of flow that the rural city was taking in, which was 300 plus 150, which is 450 maximum flow. A cut is a line drawn that must separate a sink and the source. A cut can also curve. The sum of the edge weights a cut passes is its cut weight. Highly recommend you use a pencil before drawing the final answer of your cut. Flows going from sink side to the source side do not add to the cut weight. So let's do a few examples here. Let's go with, so a cut might be something like this. Notice how if we cut this, we have the source on the left and the sink plus everything else on the right. So this is an example of a cut because we've separated the source and the sink. The cut weight of this is 10. Here's another example of a cut. We can cut through these three because if we can kind of imagine drawn in half, we have the source on the left, the sink on the right. The sum of this cut is 5 plus 3 plus 2. This is also 10. Here's an example that will really get your mind thinking about this. A cut going like this. Again, it's separating the source from the left and the sink on the right. But now, look at how I'm going to be counting this. 9 plus 3 plus, I'm missing a weight here. Let's just put this as a 1 plus 1. Notice how I don't count the 6 because that's flowing from the sink side, that's on the sink side, towards the source side. So we only count those from going left to the right. So the weight of this cut that I've just drawn is 9 plus 3 is 12, plus 11, plus 1 is 13. Here's an example that is not a cut. Cuts are allowed to curve. If you did this, that's still it's allowed to curve that way, but it doesn't separate the source from the sink because there's a flow here that still allows the source to reach the sink. Because if we follow this, it can reach the sink. So that is not a cut. Let's do that one in red. That's not a cut. Something else that isn't a cut would be something like this. Again, because there's a source for the source to get to. So I hope you get the idea of what cuts are and how to calculate the weight of the cut. And now here's the main idea that we'll be focusing on in the next video for the example. Maximum flow, minimum cut theorem states that the maximum flow of a network must equal the weight of the minimum cut, or vice versa. And the maximum flow can never exceed any cut made. This is just a whole bunch of terminology. I hope you get some idea of this. We'll do an example of what this might look like in the next video.